A matrix is a rectangular array of numbers. And you can see there's an image of a matrix right here. All of these numbers that are in the rectangular array, those are called entries. So an entry is a number in the matrix. Now, sometimes entries can be replaced with algebraic expressions or variables, or maybe you would have to like solve for an x or a y if you had like two equal matrices. Okay. But those represent a specific value or expression in a particular row or column. Okay. Let's see, you should remember this from talking about matrices last year. The order of a matrix is the number of rows by the number of columns. So we kind of write it like a dimension with a little cross X. Okay, rows by columns. And I always like to, on this, I'm going to say rows by columns up here. Just because I think you know, like, it would be very easy to swap those around, right? Convince yourself it's columns by rows or something like that. So I like to write it out rows by columns, just see that, and then, you know, like, I sort of try to take a mental picture of it. So when I'm taking my quiz or my test and I'm asked about order, I remember rows first, columns second. Rows are things that are horizontal, and columns are verticals, right? Just like the columns on a building. So make sure you know the difference between rows and columns. Does anybody remember what you call a matrix that has an equal number of rows and columns? Yes, Logan.
Square.
It's a square matrix. You know, think about the fact that a matrix is a rectangular array of entries. And if the rows and columns are equal, that's going to end up looking like a square. Okay, so will you quickly with your pods determine the order of the matrices A through D and kind of compare? I'll write my answers up here in just a moment. Okay, for A, you should have 1 by 1. For B, that's a 1 by 4. Remember, row is horizontal, so you have 1 row, but you have 4 entries, so that would be 4 separate columns. This matrix also has a special name. It's called a row matrix because it looks like a single row. All row matrices have their first dimension, or first part of the order is 1. Can you imagine what a column matrix might look like? A single column, right? Okay, yeah, and the last one would be a 1. Okay, C is 2 by 2, and this is the one where rows equals columns, so we call this a square matrix. And this also has a special name because all the entries are 0. You can also refer to that as a 0 matrix. Okay, and then D was a 3 by 2. 3 horizontal, 2 vertical. Any questions about orders? All right. Now this part where we talk about the augmented matrix next, this would be new to my students from Algebra 2. We didn't look at augmented matrices, but here's where we're going to like bring in the connection. Why does Chapter 8 matrices follow Chapter 7? Well, in the last chapter, we were working with systems of equations, system of inequalities, linear programming. A matrix that is an augmented matrix is derived from a system of equations. And what we're doing is we're taking the equations and we're changing them so that we no longer have all the x, y's, and z's, It's going to look more numerical. Matrix is a nice way for us to organize numerical data. So if this were my system, this one has 3 variables, 3 unknowns, so it has to have 3 equations. I can place that into an augmented matrix. Each row is going to be one of the equations, and then each column is going to be for a specific type of term. So since I have 3 unknowns, I'll have my first 3 columns will be x, y, and z. My last column will be reserved for a constant. Now, the one thing you want to always be really careful of when you do an augmented matrix is before you drop in the coefficients, make sure that you have it set up where all of the variables are on one side and the constant is alone on the other. So it really looks to me like I was setting it up for elimination. Okay, so make sure that you have them on separate sides. Okay. And then all you have to do is drop in the coefficients. So that would be for the first equation 1, -4, 3, and 5. -1, 3, -1, and -3. And then what do you have to be careful of on equation 3?
There's 0 y's.
Missing the y, so you got to put the 0 in. In order for it to be like in a rectangular array, every entry needs to be filled in. So if something is missing in your system, you're going to put a 0 there. So that matrix of numbers represents the system of equations. Now, also something that you need to be aware of, so that when you see it in the book or in our notes here in a little bit, you're not like, what is that? We will put in, right before that column that is the constant, we'll put in, I use colon, so just like 2 dots, to represent like this is where the equal sign in the system is. So when you're doing calculator work, you won't necessarily be able to put those colons in, but when you're writing it down or you're reading it in the book, you'll often see like in between the 2 columns this colon, which represents an equal sign. Later we'll see it in our notes. The book uses 3 dots, which I always joke I just think is excessive. So I'm only going to do 2. So I use a colon. All right, can you write the system as an augmented matrix below? I'll give you a moment to do that on your own. And then I'll put my answer up. Remember, when you're writing in the matrix, the system, you get rid of all the unknowns, the variables. Look something like that. Check your second equation, make sure you put the 0 in for the z, right? All the z's should be in the same column, all the y's should be in the same column. If you were ever to come across a system where they had them jumbled, you would make sure to pay careful attention to order. That's really important in a matrix. Okay, any questions on the augmented matrices? Okay, so now we're going to talk about elementary row operations. And it seems like we're kind of jumping around here, but eventually we're going to be putting all these things together tomorrow to be able to solve systems. Today it seems a little haphazard. Okay, but there are basically 3 elementary row operations that you can do. Okay, so here's things you can do with rows in a matrix. You can switch them. You can multiply them by something. And you can add them together. Like, those are the things that you can try to do. Okay. So we call it interchanging 2 rows. I've got a 2x3 matrix here. What you want to pay attention to today is really like the notation, like how you'll tell people that you swapped the 2 rows. So I'm going to switch row 1 and row 2. And so we're doing row 1, swap with row 2. That's the notation. It has the double arrow. And then you put the matrix right next to it and you swap the rows. 4, 5, 6, 1, 2, 3. Okay. So I'm going to be looking, like on quizzes and tests, I'm going to be looking to see that you tell me what you did. Okay, so you have to show me that you interchanged the two rows. Row 1, double arrow, row 2. I can multiply a row by a non-zero constant. I could really multiply either row by anything that I want. I can multiply one row. I mean, I guess I can multiply more than one row if I wanted to. I'm just going to do one row because we normally do one row operation at a time. And I'm going to do -4 times row 1. You see how I wrote that? -4 row 1? Okay. And just distribute it across row 1. That would be -4, -8, and -12. And then because I chose not to do anything to row 2 would remain the same, 4, 5, 6. So you're allowed to just multiply the whole top equation by -4. That's fine, or top row. Okay, now the other basic row operation that I said was adding or subtracting, but you can sort of on this one combine two of the operations. So this is going to be adding a multiple of a row. So of course I could like add row 2 to row 1 or vice versa and be done. That's an option. But I can also choose to multiply one row by something before I add it to another row or add another row to it. Okay. So I am going to choose on this last one, I am going to choose to do, I'm going to change row 2. So in my matrix, I'm going to put this down where row 2 is. What I'm going to choose to do is I'm going to take row 2, and I'm going to add -4 times row 1 to it, which is the one that we just did, -4 row 1, but I'm going to do it from here. So I'm going to write that as -4 times row 1.
Okay, if we have plus and then use negative part.
Yep, same thing. And if you wrote it as -4 row 1 plus row 2, but you put it down with row 2, that would be fine.
Would you leave row 1 by itself?
Yeah, you leave row 1 alone. So it's going to be 1, 2, 3. And you're really only affecting row 2 right here. So now I'm going to take the entry in row 2, which is 4, and I'm going to subtract 4 times row 1. So it would be 4 minus 4 times 1, which is 0. And then 5 minus 4 times 2, which is -3. And 6 minus 4 times 3.
6.
Now, what I chose to do, right? Like you could choose, like if you wanted to do, you could do any row operation you wanted. Like it didn't matter. But I'm choosing to do row 2 minus 4 times row 1 for a reason. This is like a preview into what we're going to be doing tomorrow, and we're going to get to it on the next page. It's called row echelon form. But part of row echelon form is we need a way to make zeros at the front of our rows in our matrices. We also want to have ones at the front. So we're going to choose these 3 basic row operations to try to bring in zeros and bring in ones. And we have to be very thoughtful about that. Today, you don't have a lot to do with that. Like the book will tell you what to do today because we're just like introing it. But tomorrow, you're going to have to think about how you're going to get that done. And what Cameron does could be different than what Ruby does, is different than what Andrew does, but in the end, we all come up with the same answer. So that'll be something interesting that we'll see. Okay, so next page talks real quickly about row equivalents. Basically, it's just saying if you use those 3 basic row operations that I just gave you, you're making your matrix look different, but essentially your matrix is holding the equality of the original system or matrix. Okay. So this is an example of like what you might see in the textbook tonight. It will give you a matrix. Notice how this one is an augmented matrix, so it represents a system. We can see that because it has the colons, and notice how the book uses 3 of them. Okay. And you will be told tonight what to do for row operations. So you just need to practice writing out the notation, telling us what you did, and then performing the row operations. So let's do those real fast.
Is there an order of operations for these as well?
You're going to follow them in the steps that they say. So step 1, switch row 2 and 3. So which row doesn't change? Row 1. So I will copy row 1 as is. I will make a notation outside of my matrix for my swap. Row 2 switches with row 3. And then I will switch the 2 rows. So 2, 0, -4, 6 will be my second row, and -1, 3, -1, -3 is my third row. And then if they give you more than one step, now you're going to continue. So we've done step 1, which is switching rows 2 and 3. Now we're going to continue with that matrix. We're going to add row 1 to row 3. Okay, think about the directions there. Add row 1 to row 3. Which row are you changing? We're changing row 3. So row 1 stays the same, row 2 stays the same.
Which matrix are we going based on?
We go off of the last one we did. So we're using the new one where we switched row 2 and row 3. And now for row 3, I'm going to do the addition. So I'm going to make a note off to the side. This is row 3 plus row 1. If you write row 1 plus row 3, that's the same thing, right? Doesn't matter which way you write it. All right, and then add. -1 plus 1, 0. 3 plus -4, -1. -1 plus 3, 2, and -3 plus 5, 2. Yes, ma'am?
So you keep like the first row even though you added it to the third row?
Yes.
Okay.
Because, like, I always think about, like, when I read this direction, which row am I changing? I read it as add row 1 to row 3, so I'm changing row 3. So then 1 stays the same, I just copy it. Yeah, and I would really, really recommend that you only try to do one row operation at a time. Every now and then, people are like, well, I'll just move this along a little quicker by doing a few row operations. I'll change row 2 and row 3, and that just sort of makes a big mess. So it's better to just take your time and go slow. I know it's a lot of like space that they take up, but probably gets the right answer faster.
Will there ever be one that's like combine row 1 and row 3 to make it into one matrix? Like one
No.
row?
Combining them would be through addition or subtraction. You have only 3 row operations.
Okay, so
Switch, multiply, add, subtract. Okay. And then notice again, we're gonna stop there. I'm not gonna do a whole bunch, but like in the book, it might have like a few more steps for you to do. So you just continue off of this one. Okay, this last one you did. But notice how again we did it so that it's introducing that 0 in the front. So that is something that like you can kind of set your eyes on for like, I'm gonna need to be able to do this tomorrow. What row will I multiply by what or combine or switch around so that I can get these zeros and these ones? Okay, last thing we want to talk about is called row echelon form. Tomorrow, if you bring your graphing calculators, we will also do some matrix work in the calculator. And in the calculator, we'll be able to identify the call for row echelon form as REF. The bullet points listed below are the characteristics of a matrix that is in row echelon form. So I will write the characteristics and then I will draw you an example matrix. Okay, it is in row echelon form if any row of all zeros is at the bottom. Now, I'll be real honest. If you're solving systems like we're going to be doing, you don't encounter rows of zeros very often. But if you do, you put them at the bottom of the matrix. Okay. All other rows have the first non-zero entry equal to 1. So your first entry in your row can be a 1 or a 0 or multiple zeros, but after all the zeros has to be a 1, no other number. So your row could look like 0, 0, 1, other stuff, okay, or 1, other stuff. The first thing that's not 0 has to be a 1, is what that's saying. And then this last one says for 2 successive, which just means like 2 rows right after each other. For 2 successive non-zero rows, the leading one in the higher row, so in the row above, is further to the left than the lower row. So what you're going to see is in your matrix, and I'll draw one here in just a second, your ones like are going down on a diagonal from, what is that, left to right for you guys? Okay, and like sometimes one of them is missing, that's okay, but they have to be like moving over to the right as you go down the matrix. So here's an example of something in row echelon form. I'll do 1, 2, 3, 4, 0, 1, 2, 3, and I'll do 0, 0, 1, 2. That's row echelon form. If I had a row of zeros, they would have been at the bottom of the matrix, but I don't have one. So you don't have to have a row of zeros. Okay. All the other rows, the first term that's not 0 is a 1. So notice it starts with a 1, then it goes 0, 1, then it goes 0, 0, 1. So that's called my leading 1. Okay. And then if I check my rows, if I compare like 2 rows, row 1 and row 2, the 1 in row 1 is further to the left than the 1 in row 2. So the higher up you are, the further to the left your 1 has to be. So that's row echelon form. And then tomorrow we'll also talk more about row echelon form and reduced row echelon form, which in your calculator is going to be an RREF. So there's a difference between REF and RREF. In a reduced row echelon form, the zeros are before and after every leading one. Before and after every leading one. So that would mean basically your matrix is made up of ones and zeros. Yeah. Now, there is going to be like an exception to that. So like here's an example of reduced row echelon form. Oh, here, I'll just make that one a row of zeros. That's fine, right? It's on the bottom.
So after the 1, everything after the 1 is 0?
Yes, except tomorrow, when we do it in our calculator, notice this one is square, right? But if we're doing an augmented matrix and we're asking our calculator to do reduced row echelon form, you are going to see some that look like this. So the leading one is followed and preceded by zeros, except for the constant in the augmented matrix might be something other than 0. And we'll talk more about that tomorrow. Just let that sit.
So then it's just the coefficient of the variable then.
Yeah.
Augmented, the constant can be whatever.
Yep. We'll talk more about RREF tomorrow, but I just wanted to put it out there. Okay.
Wait a minute.
Okay, so by hand, without a calculator, reduced row echelon form is a lot of work, right? To get like a 1 in the front and then a 0 all behind it, or a 0 and a 1 and all zeros. But without a calculator, row echelon form is reasonable. So like as we go into tomorrow, what we're looking for is can we choose row operations to get row echelon form? And if we do, then we can solve a system. Tonight, you don't have to worry about coming up with your own row operations. The book will tell you what to do, okay? But you will have some problems that are prepping you for tomorrow once we get them into row echelon form. So look at this last example on the second page. Do you see this augmented matrix? represents a system of equations, and it is already in REF, row echelon form. It has leading ones. The ones are moving to the right as we go down the matrix. We don't have a row of zeros, but it would have been at the bottom. Okay, if you already have it in row echelon form, then you can solve the system very easily. Take your augmented matrix and turn it back into the system of equations it once was. So put the x, y's, and z's back. X minus y plus 2z equals 4. Y minus z equals 2. And z equals negative 2. Here's the benefit of row echelon form. If it's in row echelon form, your final row will likely be a row where you know the value of one of the unknowns. So we know z is negative 2.
So in reduced row echelon form, if it's like it was up there for the augmented, wouldn't we know what all the variables are?
Yes. I'm going to talk about reduced row echelon form tomorrow.
Oh.
But I'm not going to say a whole lot about it today other than what I defined. So I'm moving on and I'm doing this problem right here. Okay. So z is negative 2. If you knew that z was negative 2, would you be able to find y and x?
Yeah.
Yes, how would you do it?
Plug it into the same.
Sub it back in. Okay, now I'm going to use a phrase right here. I'm going to say, because I'll talk about this in the matrix unit a lot, I say use back substitution. If you're reading in the textbook, they call this like Gaussian elimination, but it just means like plug stuff back in. I just want you to be comfortable when I say use back substitute it. I just mean plug it back in until you find it. So we'll say y minus negative 2 equals 2. That's y plus 2 equals 2, therefore y equals 0. Got it? Then we'll back substitute again with our y and our z. X minus 0 plus 2 times negative 2 equals 4. Be real careful here. This is x minus 4 equals 4, and x is 8. So do you agree that if it's in row echelon form, finding the solution to the system is very fast? Okay. There are going to be some problems where the book will tell you the row operations to get to row echelon form, and then you will solve the system from there. And then I think they have like a part B where they say solve the original systems. Then you're going back to your chapter 7 knowledge. You can solve by substitution. You can solve by elimination. So you solve it algebraically like we used to do. And then in part C, it's going to say like compare the two solving methods. Which one do you prefer? And all I want you to be thinking about is back in chapter 7, we could solve by graphing. We could solve by elimination. We could solve by substitution. We had all those X's, all those Y's in the mix. And now we're going to do the same thing, solve the system in a matrix with this rectangular arrangement of numbers. All the X and Y's are gone. You just have to get it into row echelon form. Do you like that? Do you prefer it algebraically? Okay, it's just a comparison of different ways to do the same problem. Okay? All right, we've got a little over 10 minutes, so I expect everybody to get out that textbook at your pods and get started on your problems.